siglo aportando al desarrollo social e industrial de Chile. Un siglo liderando la formación de ingenieros e ingenieras para un nuevo mundo. 9 departamentos académicos gestores de conocimiento para la sociedad y los sectores productivos. 11.000 estudiantes. 15 ingenierías civiles acortadas a 11 semestres. 8 ingenierías de ejecución. Universidad con 7 años de acreditación. 72 laboratorios de alta tecnología. 10 programas Centro de Investigación con Impacto Territorial. 12 programas de magíster. 4 programas de doctorado. 391 convenios internacionales. Centro de Innovación con tecnología única en Sudamérica. Perfil de egreso internacional. El sello USACH que soluciona problemas reales de las personas y se compromete a seguir fortaleciendo el desarrollo del país. Ya es un siglo y así seguiremos. Aportando a la ingeniería del futuro.
Ahora sí, entonces, muy buenos días a todos y todas. Nos encontramos el día de hoy para poder conversar con respecto a inteligencia artificial, para conversar con respecto a la red y también como una de las primeras actividades que nosotros nos constituimos con respecto a este trabajo que esperamos sume a más personas y conversemos y veamos cómo nos posicionamos nosotros como universidad en estos temas. Esto también aprovechamos la visita de Fred. Fred nos va a acompañar y nos va a dar una charla un poco más adelante, pero vamos a aprovechar este contexto principalmente para entender que las necesidades hacia la transformación digital, hacia el uso y la importancia que tiene la inteligencia artificial en el desarrollo permiten situarnos y evaluar cómo nosotros vemos estos elementos y a partir de eso cómo podemos usarlos para nuestro beneficio y apoyo. Obviamente a partir de eso, desde el año pasado estamos en conversaciones con algunos colegas y tuvimos la primera reunión en enero. ¿Ya? Esta primera reunión en enero enmarcaba conocernos, empezar a planificar y situarnos bajo una perspectiva, porque nosotros la llamamos la red académica de pensamiento para democratizar la inteligencia artificial. Y en ese sentido, nuestro objetivo siempre va hacia las personas y desde el foco también de nosotros como una universidad estatal y pública, cómo nos situamos en esos espacios y cómo visibilizamos y cómo atendemos y abarcamos la mayor cantidad de personas que pudieran serse beneficiarias, a lo mejor. Y muchas veces este beneficio ni siquiera es un beneficio directo, sino que es un beneficio indirecto, que eventualmente podría terminar en un mejoramiento de la calidad de vida de las personas. ¿Ya? A partir de eso, entonces, nosotros tomamos este espacio como la primera instancia formal. Nosotros ya con algunos colegas nos hemos comenzado a reunir, a pensar, a tirar algunas líneas y queremos sumar. Y bajo el espacio de sumar es generar espacios para presentarnos, para que nos conozcan y después de eso convocar. ¿Ya? Entonces, para la presentación de nosotros que tenemos con respecto a la red, tenemos principalmente una visión y una visión que se enmarca fuertemente hacia dónde queremos llegar. ¿Ya? Y esperamos que esta red y la universidad sea un líder regional en la democratización de la inteligencia artificial, promoviendo el acceso equitativo y la educación y la aplicación ética de la inteligencia artificial en la sociedad. Esto es un ethos, es un núcleo que nosotros tenemos para poder situarnos en estos espacios. Obviamente muchos otros centros y grupos están viendo distintas formas de ver la inteligencia artificial y esto también lo vemos como un espacio y un nicho específico que nos caracteriza también a nosotros como universidad. ¿Ya? En el marco de eso nosotros tenemos 4 ejes estratégicos que esperamos desarrollar. Alfabetización, ética, por supuesto, interdisciplina con foco hacia las aplicaciones en distinto nivel y finalmente un fuerte trabajo en la divulgación del conocimiento y esta es una de esas instancias en donde nosotros nos situamos desde la divulgación del conocimiento. A partir de eso nosotros tenemos acciones estratégicas que esperamos desarrollar, acciones estratégicas que están en el marco del corto, mediano y largo plazo. Tuvimos una reunión eh, intensa para poder visualizar estos espacios y entender que hay cosas, que esto se enmarca en un elemento global, pero eso tiene bajadas concretas. Por ejemplo, cuando nosotros hablamos de diseñar un plan de formación en IA para la comunidad universitaria, eso es un largo plazo. Sin embargo, existe el conversar, cómo nosotros podemos incorporar elementos de inteligencia artificial para la comunidad, para funcionarios, para académicos, para estudiantes, a partir de pilotos, a partir de estrategias particulares, a partir de, por ejemplo, vínculos con desarrollo de personas, que permite entender que el desarrollo funcionario pudiese también a tomar este tipo de herramientas para un aumento de la eficiencia o mejora en la calidad del trabajo de cada uno o cada una de nosotros. Por otro lado, apoyar lineamientos para incorporar la ética en IA y cómo se puede incorporar para proyectos en inteligencia artificial. La conversación con el comité de ética actual que tiene nuestra universidad y a partir de eso generar lineamiento en cómo la inteligencia artificial abarca y aborda estos elementos y cómo a través de la red podemos apoyar esa iniciativa sin competir, porque nosotros no es la gracia. Establecer colaboraciones institucionales con instituciones locales, obviamente, ¿por qué? Porque necesitamos probar, necesitamos la data, necesitamos generar estos espacios para poder generar distintas herramientas acá para poder solucionar. Un CESFAM, por ejemplo, pudiese ser una alternativa, cómo podemos incorporar esos elementos para estudiarlos, de entender procesos, etc. Organizar eventos, que es como lo que estamos haciendo ahora, pero principalmente la divulgación pública del conocimiento. Facilitar la creación de grupos, ¿por qué? Porque esto esperamos que abarque a muchos y muchas y no solo... y que nace de la Facultad de Ingeniería, nace el Departamento de Ingeniería Informática, pero queremos que crezca y que sea un espacio interdisciplinario para poder abordar estos desafíos. Y finalmente evaluar las necesidades de software de IA en el campus y cómo nosotros podemos trabajarlo, a partir de esos elementos asociados a algo que a lo mejor le toca más directamente a los estudiantes, que cómo nosotros podemos evaluar el plagio y cómo se puede incorporar la variable de si hago la tarea, yo puedo detectar que esa tarea la hice yo o la hizo ChatGPT, por ejemplo. ¿Por qué? Porque una cosa es entregar eso y lo otro es el desarrollo del pensamiento crítico, que es la variable siguiente que nosotros esperamos, que nuestros estudiantes tengan el desarrollo del pensamiento crítico para poder definir y discernir qué es lo que me entrega un prompt versus lo que yo necesito. ¿Ya? Pensemos, yo siempre lo he tomado como una perspectiva de que ChatGPT, por ejemplo, ChatGPT o cualquier inteligencia artificial es como la calculadora 2.0. Pasamos del abaco a una calculadora y esto que también es una herramienta y tomarlo como una herramienta, pero bajo una perspectiva ética importante. Ahora, ¿quiénes somos? Esta es la foto que nosotros nos tomamos, la primera foto, la primera reunión, donde lanzamos acá, éramos pocos y hemos ido creciendo y queremos sumar muchas personas más. Esta es la reunión que tuvimos en enero, fue la última casi actividad que tuvimos antes de cerrar el boliche e irnos de vacaciones, pero queríamos marcar ese hito de inicio en enero para poder partir y continuar trabajando durante marzo. Y sí, durante marzo hemos trabajado fuerte y arduamente con colegas, con otros que no pudieron participar en esta parte, pero sí con otras personas que se han ido sumando para poder ir entendiendo y que radica en esta pequeña presentación que conlleva y que trabaja con respecto a la red. Ahora, ¿queremos sumar a la red? Por supuesto. Así que pueden, si ustedes quieren, ingresar a ese QR se va a transformar también en un link, ese link va a estar disponible, vamos a enviar, va a estar la nota, va a haber una nota de este evento, por supuesto, y ahí va a haber un link para sumar personas, es un formulario de Google, y que permite incorporar más elementos, y no solamente desde el punto de vista desde lo técnico, de los fierros a veces hablamos, sino que también desde las aplicaciones y del uso directo como usuario, o quiero entender, quiero conocer más, o cómo me voy sumando estos elementos. Así que estamos dejando unos pocos segundos para que se vayan sumando, pero lo importante es que esto también va a estar disponible, nosotros vamos a disponibilizarlo, como les comento, para que se puedan sumar, para que puedan ser parte y conocer más con respecto a lo que estamos haciendo, y lo que más necesitamos son manos, porque hay hartas cosas como les habíamos planteado, que queremos hacer, que queremos desarrollar, así que eso es la red. Era una pequeña presentación que le teníamos para hoy, porque lo importante ahora es el plato de fondo, que es Fred. Así que en este momento les dejo a Fred Hamken, que es profesor de Artificial Intelligence de University of Technology Chemnitz en Alemania. Él va a hacer su presentación de Mind Means Machine, Exploring the Symbiotic Relationship Between Neuroscience and Artificial Intelligence. Él viene con una visita con el profesor Javier Baladrón. Han estado trabajando arduamente, así que tomaron este espacio para que podamos conocer un poco más de lo que Fred hace. Así que, Fred, bienvenido. You can come in. Welcome. Yes, it's your turn. And thank you. Muchas gracias.
Hey, buenos días. Me llamo Fred Hamke. I have to speak in English. Usually we start with English in school and then choose between French or Latin, and Spanish is somewhat later. I had a course in Spanish, but I didn't take it for too long, so I have to speak in English. So I'm happy to hear first time in Chile. And I saw a little bit around here, this town, and some neighboring cities. I will later pass on to a conference in Toucan next week. So today is then the topic I was introduced already. So let me then start with first, when we talk about artificial intelligence, what is it? You see it often in the media. But there is nothing like the artificial intelligence. So intelligence it's rather a toolbox with lots of different tools, and I don't know if you can read these words. There's many of those, and there is not even 1/10 of it. There's many more disciplines that make up what we label as artificial intelligence. But and then people necessarily have not overlapping fields. Some researchers are working on completely fields and then others. But why artificial intelligence became so popular recently is because of neural networks. So let me then have a little history of neural networks. So it's actually known for a little bit more than 100 years that the brain has actually neurons. And the first models of neurons are somewhat developed in the 1960s, but then these little networks didn't really solve complicated problems, and then there was a loss of interest in this field, which is called the Neuro Ice Age. But then in the mid-70s, researchers discovered new networks, new learning algorithms, and it was somewhat a Cambrian age, a Cambrian explosion of a large number of different types of neural networks, and also the so popular now backpropagation learning rule was developed during that period. But then after a while of enthusiasm, other networks, not really like neural networks, but rather statistical learning machines were developed, so-called support vector machines and other methods. And then there was again some loss of interest in neural networks. It was still a serious tool among other tools of the field of artificial intelligence, but not the major discipline. It probably is now a major discipline by a recent enthusiasm about deep neural networks. And in fact, they still function based on the principles developed in this phase. For example, they still learn by backpropagation learning. The researchers just find out a number of tricks to make large networks stable. So in the beginning, if you build larger networks, they became unstable in learning. And now due to the development of these tricks and more modern computer technology, you can now design huge networks with millions of parameters you can then train over time. Yeah, and we will see how steep that period is still going. We now have also transformer neural networks, which are often in the media now. And in parallel, a discipline has developed which is called computational neuroscience. Computational neuroscience is more focused on trying to understand brain function. So these neural networks are inspired by brain function, but this discipline doesn't aim to understand how the brain works. It just tries to build intelligent machines based on similar principles. And in fact, my PhD was during this time, so just before 2000. And at that time, I was interested in designing neural networks that do not suffer from catastrophic interference. So what does this mean? If you train a neural network and then have a different data set and train it again, it tends to forget the previous knowledge. And that is, of course, a bad idea. And I try to design algorithms based on growing neural networks that somewhat solves this problem. It worked fine, but the field moved on and they don't really care. What they do, they just set up a big database, and then if there's new data coming on, they mix it and then do just train the network again. So why I'm saying you this, not reporting so much about my PhD, I want to tell you this example because sometimes the optimization goals of machine learning and living organisms are different. For example, no living organism could have an interest of carrying a database of data around. So it has to learn immediately and then, of course, has to keep that knowledge while learning something new. So this leads me then to the question, in how far do we have a neuro-inspired artificial intelligence, or is it just the opposite, that artificial intelligence inspires neuroscience, or inspires how we understand the brain? We have to say that artificial intelligence has always been somewhat inspired by psychology, neuroscience, some brain research. So that's certainly valid. But the question is there really a strong link between these disciplines or just a more weaker link? And some research favor a more stronger link, like one of those. Gershman is rather a little bit more negative and says, well, it's more separate disciplines. And some researchers suggest to bring these fields more together to design a kind of embodied Turing test, but then the question is, should artificial intelligence be interested in that? Usually they try to solve problems, whatever they define as a problem, and then put in their effort to solve this particular problem. And the question is, would these researchers be interested in designing a little animal robot? It's maybe more like a fun project, but maybe there's also time to earn money with that, then probably they will start doing that. Let me give you a number of examples where I think now there is an exchange, in what kind of direction is this exchange. So example 0 is called 0 because I think that is not a good example, but I still want to include that because it's about transformer networks. Transformers, GPTs, and you know ChatGPT, which is built on these technologies. And I didn't really find a strong link that is supposed to be here on what should be a complementary thing or mechanisms going on in the brain. So of course there's some relationships, they work on neurons and all these things, but the particular techniques of training, these large language models try to forecast or predict next words, But this type of language understanding is different from human language understanding, which is more about transferring ideas, intentions, which these machines don't have. So let's move on to a more serious example, and this is about reinforcement learning. So reinforcement learning is a quite good example because people like Bartow and Sutton were trained computer scientists, but they also had some relationship to psychology, for example. And they got inspired by fields of instrumental conditioning. If you train animals, for example, if you have dogs, you permanently do this instrumental conditioning by food, that they behave well, and so on. And they designed a kind of actor-critique architecture, which became the building block of modern reinforcement learning. So here, there is certainly some inspiration from the brain going on. And this kind of temporal different learning architecture then also inspired the design of Q-learning techniques. So here I have the basic equation of Q-learning. Why is that important? Q-learning allows or gives each state action pair a value. And you can update that value by exploration and exploitation in the environment, just exploring your world. And while you're exploring, you learn to know a model of the environment. Also, you learn to know a policy that you can optimally act in this environment. And the nice thing is you don't have to look ahead with this. So it caches all the important information in these values of these state action pairs. And you don't have to search and plan ahead for long periods of time, which classical artificial intelligence had to do in planning algorithms. And that is a nice thing of reinforcement learning. And nowadays, many researchers even try to take these reinforcement learning algorithms to somewhat try to understand brain function. So, for example, that the state actions could be stored in cortex, and maybe the basal ganglia, which you see here, is doing some form of action selection or decision making. And then this is also linked to the dopaminergic system. You probably heard about the neuromodulator of dopamine, and that is supposed to be some kind of reward prediction error. And there's certainly some relationships going on. So that somewhat this field works in circulation, but maybe even since people didn't understand that complicated circuit in the brain yet. So therefore, people now use machine learning to somewhat make sense of the brain. That's why I made that error a little bit more thick than the other error. And the nice thing is that also these kind of, the target and the prediction in that equation can be predicted by deep neural networks, and that made that technique also very successful nowadays, although it was first used more like with tables. So another field is episodic long-term memory. People have thought, for example, now that the hippocampus could also function like an autoencoder. So hippocampus is here, it's underneath the cortex, and it has the ability to rapidly store episodic encounters. So even when you see something the first time it is important, you tend to memorize it. Maybe later on part of that knowledge is transferred to cortex, but initially hippocampus is something like a storage device. Maybe it has additional functions. And yeah, so some researchers propose that maybe the CS3 is somewhat the compressed state space, and the input is the entorhinal cortex, which is this part here in the figure, and then you then project back into the entorhinal cortex as well, so that it has a kind of autoencoder-like structure. Yeah. So therefore, again, this error is more into that direction rather in the opposite direction. It is not like understanding the hippocampus has revolutionized AI. Another example is this little circuit again with the hippocampus. This circuit implements attractor dynamics, and it can store knowledge, and in a partial cue can reactivate that knowledge. It's kind of like an imagery. Once I give you a little hint, then the whole memory lights up in your brain, and then you know where to go, what you see, and so on. But again, that hippocampus has not revolutionized AI. An example where also much exchange is going on is in the field of vision, image processing, and understanding. For example, there has been some inspiration of these deep neural networks with understanding of what is a receptive field in the brain, that the information is distributed, stored in the connection of all of these weights rather than in a separate storage device, and all these things. But then once these researchers in artificial intelligence and neural networks understood that main principles, they moved on in their own way, and they forgot about details of how the brain may work, and rather built successful huge networks which rather operate in a feed-forward sweep. So now people started to take this network and trying to understand again how the brain works. So many vision researchers that came from neuroscience psychology now also play around with these deep neural networks. But there's some differences in these networks. For example, these deep neural networks are sensitive against context. So this is an example where a neural network was trained on a database, and when you present this kind of figure here with a motorbike and a monkey, it tends to say that the monkey is a person. So why that? Because the combination of motorbike and monkey is rare in that database on which that network has been trained. It rather has seen humans and motorbikes. And it doesn't understand this distinguish. It cannot distinguish that. So it tends to use every pixel for its final output, and the combination of motorbike and something that looks like a human must be a person. It cannot be a monkey. Of course, you could fix it by giving this other examples when you show monkeys with motorbikes and then label this data properly. But it shows that it doesn't have an understanding of the world. It's just crunches a lot of number of training examples. And here, this is a bird here from the bike here, maybe because it's so green in the background, and even the guitar is the bird for that neural network. Also, you can trick these neural networks in a very strange way, which is called these adversarial attacks. So if you present this image, it's classified as a cat, sure. But then you can use other networks to fool this network. So these other networks generate patterns that are overlaid on top of this, which is hardly seen by humans. For a human, you see no difference between this image and this image. But tiny things have changed, and it has been optimized by another network to fool exactly this network to become totally out of control. Of course, you can also find remedies for that, but it really shows that these neural networks operate somewhat different than the brain. So what is different? The brain has lots of recurrent processing. All of these networks are interconnected to each other in a forward and backward way. There's nothing like a clear forward pathway. Of course, you have some brain areas that receive more sensory inputs, but in the end, it doesn't really converge to something. So it's hard to tell. Further, all of these little networks are also implemented in a massive recurrent interaction of excitation and inhibitory neurons. Some people have started now to now build deep neural networks, and they try to incorporate some ideas, for example, feedback connection, into these deep neural networks. And what is interesting here, if you plot the performance of these deep networks and plot the similarity of brain function measured by a so-called brain score, you can generate deep networks like this CoreNet, which is here, that has a high brain score, but it's still operating quite well. Maybe it's not the best network, and it's not taken now in the artificial intelligence community as a reference network, but nevertheless, it's kind of interesting to see that some principles of brain function may be incorporated into these deep networks. But we're still far away from understanding these kind of highly recurrent dynamic interactions, and we probably also still don't have proper learning rules for that. So we also worked in that field, and we tried to see how far we get with pure unsupervised learning. So all of these classical networks in artificial intelligence are trained by supervised techniques, that you have some kind of teaching signal, and therefore often you need therefore labeled data, but you have some kind of teaching signal that is given to the network by a human, and then that network is trained on these examples. So the networks we designed are trained fully autonomously. You don't give them anything, you don't even let them explore in the environment, you just show them samples. And nevertheless, some useful pattern just emerges from the statistics of these inputs, and actually we made it work that we can train a highly recurrent network. So the performance of these networks still don't converge, that are competitive with these deep neural networks, but it's not surprising because we don't give any supervised label into these networks. To make it perform more functionally, we somewhat extended a high-level representation which has a label of a brain area called infotemporal cortex, and map it into another part of the cortex called prefrontal cortex. And in actually, this mapping from here to here can be trained on another network, which we implemented as an example of the so-called basal ganglia, a kind of reinforcement learner, a biologically inspired model of reinforcement learning. And actually the funny thing is that this one receives this kind of dopamine signal, this reward prediction error, and can train now this connection. And we showed it that it works for artificial examples that were also used for studies with monkeys. So brain science, and we also used it to classify faces of 2 former US presidents. And the interesting thing is that this machine works like a very fast learner, which alone doesn't function so well, but in combination has optimal performance to classify these images. Of course, these are just a small data set. We didn't test it on very large data set yet, but it's an interesting example that a fast learner can be trained in combination to a slow learner. So the slow learner is the cortex and the fast learner is the basal ganglia. So let me now show a video of a European project we once did. I only have the sound on the computer, but I just let it run and see. Yeah, so I was a coordinator of this European project Spatial Cognition, and as you might have seen, the focus of research was here that we probably have to store or compute our sensory inputs in different reference frames. For example, vision is with the eyes, so it's retinocentric. Hearing is with the ears. They are attached to the head, so they are head-centered. And if you want to converge these devices, we have to transform one space to the other. And we also want to act in the world. When I want to grasp something, I do this with the body-centered reference frames. And when I walked around, I have something like an allocentric reference frame. For example, a map. When you see a city map, and that is, and you locate yourself in that area of space, and something like space cells, place cells have been described as one of the recent Nobel prizes by O'Keefe and another person in Norwegian. I cannot recall that name now, but it was indeed a recent Nobel Prize about the discovery and understanding of these place cells. And we built networks based on these kind of principles, that you combine vision with memory, can store, for example, can store this device here on the table, and then you go back and have a memory recall, and then go back to your originally stored location and can pick up this object. And that network is shown here. It has a vision component, saccade selection control, eye movement control. It has components to make transformation from one frame of reference to another frame of reference, and it has a kind of model of the hippocampus as a storage device. And that is a completely neural model. It doesn't solve everything, but at least it's a large-scale neural networks to demonstrate that brain's research can actually be useful also in creating agent. Of course, I admit we cannot compete with full-fledged machine learning approaches in this field, but nevertheless, it's nice to demonstrate that these networks we are designing, which are inspired by the brain, can actually do some kind of function. And here we now see the top view. No, I have to start that movie. Whoops. We have the top view of the agent and the egocentric view, how it walks around. And then it looks at an object here, memorizes it in its memory, goes to another location, and then goes back. And on the right hand side you see some kind of maps that show activity of this neuron that somewhat control this little agent to do its actions. The walking itself was not controlled by the model, also not decisions making. So he had to solve a particular task, and then that was executed, and finally he went back to this object and foveated it. So we all do this also using simulation techniques, parallel computing device. So we designed a neurosimulator toolbox called Anarchy, which allows you to simulate spiking and rate-coded neurons. And in fact, you don't have to be an expert in this kind of programming. This simulation tool takes over lots of works. So let me summarize now, and coming back to the question about are these different disciplines or common disciplines that exchange each other. And I would like to propose you 3 examples where I think in the future there could be even more exchange than in the examples I've shown to you. One is about neuromorphic computing. So these deep neural networks require a large amount of energy and memory. And as you know, computation in the brain is very energy efficient. You sometimes need to eat a little bit, and that's it. And also this kind of event-based computing may reduce the costs of information transmission. So event-based computing means that the neurons, if you simplify them, they simply generate a spike in action potential, and then this is sent out to all the receiving neurons. And indeed, it got some interest for big hardware companies. So they are building specialized chips, specialized hardwares. Here's a few examples, Intel, Lohi, and so on. They do not allow everything yet, but at least the interest has started in these big companies. And there's also very small startup companies entering this field. And that could be particularly relevant for mobile systems, for example, cars and robots, which actually don't want to store all this computing power and therefore need this kind of small scale energy efficient devices. And I think there could be a nice exchange between these different fields. Another field is cognitive computing and problem solving. So because present AI, although it's very powerful, it doesn't really generate knowledge. It doesn't invent knowledge. The knowledge is given by humans to these machines. They simply store it and make something interesting out of it. Of course, they learn from examples, and you could say, yeah, they learn by playing against their self, creating new memory to new solutions. That's true, but this is simply domain knowledge. This is a small field. If you take a machine, let it solve a certain task, and then place it to a completely different task, it will totally fail. So that is what I meant with problem solving. So we have the capacity of creating new knowledge. Engineers, scientists, artists. Of course, you also see now AI creating art, but well, they have seen millions of examples of human art before they actually can do that. And therefore, I think in this field, understanding cognition and the brain may probably, we don't know yet, but may probably lead to different neural networks, different learning algorithms that could maybe do more complicated tasks than nowadays. And the final one is neurobotics. Because the present wave on AI didn't inspire so much or didn't lead to major progress in robotics. So why is that? Maybe robots need to learn more by themselves, by interacting with their environment. Maybe in that field, it's somewhat difficult to just give them examples generated by humans. And therefore here, for example, solutions like body ownership. Robots usually don't have an understanding of their own body, what we do have. Or agency. Usually we are aware that somebody did something in the environment. Robots don't have this feeling of agency. And also observational learning. When we observe somebody doing something, we can already get an idea. Okay, what should we do in order to be successful in a particular task? And these are all examples which are not present yet in artificial intelligence, but these are nice examples we could study to maybe have more progress in these disciplines. So thank you very much.
It's okay. Can you hear me? Okay. Thank you very much for the presentation. Just in one slide, you show a very interesting activity in the last years of the artificial intelligence community. Can you go to that slide, please? It was one of the first. Sorry? No, it wasn't at the beginning. It wasn't at the beginning. It was at the beginning. Yeah, the one of the history. Yeah, that one. So that one, exactly that one. So my background is mostly civil and mechanical engineering, and usually those jumps could be easily explained because of hardware evolution. So, for instance, many of the algorithms that we are using are usually very old. But at the beginning, or when they were developed, there was not enough hardware to implement it in applications. Could you say that the same applies to these jumps? For instance, novel network models, learning, backpropagation, and so on, deep learning, are also associated with the evolution of the hardware?
Stable, that they don't forget all this knowledge. I don't want to go too much into detail, but skip connection or you erase some connection. It's just tricks or they change activation rule. Usually in the past it was a sigmoid, but then it also has some problems in that in the end the gradient for learning is too small to let it converge properly. There were many small tricks that made this learning possible, but in addition, only with powerful hardware. And yeah, the question is now, will there be also maybe for brain-like devices, will there be also more powerful hardware that could also maybe help that disability? Because nowadays, it's usually mapped onto classical von Neumann architectures, but these more brain-like hardware is not optimal Yeah, good question. I was already surprised. I thought it would end here, but then there came this transformer neural network. So I was surprised by them. I didn't expect it. I thought it will go down again because deep networks are powerful, but they are very limited. But these transformer neural networks, well, gives it a high punch upwards. I think cognition is still a problem, but as you see with GPT, and now I've heard about also visuomotor transformers, people are now trying to use these transformer techniques also in robots. There is still a little bit space to go upwards, but then we probably need new techniques, and we will see if they're discovered or not. So it's hard to foresee if engineers come up with a new network or if we get stuck with a transformer technique, which has its limitations and leads very large devices to train all these things. Yeah. Yeah, there's a community that is interested in trying to bring these fields together, understanding brain and AI, because in the end, I mean, the brain is still the example of artificial intelligence, of a very sophisticated artificial intelligence. Of course, if you think about societies, maybe something also wrong with the development of the humankind, but it's another point. It's not an issue of this talk here. But in terms of flexibility, it is the human brain is much more superior to artificial intelligence. Of course, in specialized tasks, artificial intelligence can even be superior to the human brain. That is for sure. But I think the combination of both might be interesting, but it requires a better understanding of brain function, and progress is visible, but it's still slow. There's no major breakthrough yet. But when I say slow, it's always relative. I mean, sometimes you are surprised when you look backwards what all happens. No? But if you look forward, you somewhat think, well, it's all very slow. But sometimes things change quickly.
Yeah, I have a question. You mentioned the transformer and the GPT that are superior to the deep learning, but I don't understand why they are that superior in comparison to the previous one.
Yeah. So these transformer techniques can be learned in a self-supervised way. They are therefore called large language models. So the simplest thing is that they have a kind of network prediction. You start with a sentence, today I'm going home and eat, and so on. And you can then always predict the next word based on the context information you have. And these networks have many layers on top to store huge amount of context information that allows them to do these kind of predictions. That makes them very powerful, and you can easily train them on the whole internet, all the data. You can also train them on programming languages and all of these things. You can also use these kind of techniques to do image processing. It's a little bit surprising because, I mean, they don't understand language. The words are transferred into tokens, and then they operate on that. But you can transform everything on these tokens. You only need a kind of sequential relationship. That is all you need in the data. Whenever you have this, you can use this kind of prediction techniques.
Thank you.
Thank you very much, Fred, for your presentation. Very nice presentation. My name is Leo. I'm a colleague of Javier. So in this relationship between neuroscience and artificial intelligence, I'm guessing that the context is always a healthy brain, right? So you mentioned very high order brain functions, right? So I was wondering, what can we learn about pathologies using artificial intelligence? Or, I mean, because in the computational neuroscience field, I know that people are using biophysical models to understand certain pathologies, say Parkinson's disease, Alzheimer's disease. But can you use these tools to understand how the brain function in certain pathologies?
So to use artificial intelligence
Artificial
tools
intelligence,
in brain research? Yeah.
Yeah.
Yeah, I mean, that is quite often being done. I mean, for example, you collect lots of data and then use these artificial intelligence tools to make sense from that data. You also use this, for example, in brain-machine interfaces. When you connect the brain to some kind of device that can, for example, help you just by your own thoughts to control a robot arm that gives you something to drink and so on. that is actually also used. Yeah, machine learning tools are used also in the neuroscience domain, definitely. I mean, but these are just supporting tools. They don't, here in my talk, I rather was targeting the question in how far could machine learning help to understand, or these models, the function of these models, help to understand brain function. And that was a little bit different than these could be useful tools in going through this progress of understanding of the brain. I mean, certainly machine learning tools are heavily used in the neuroscience community, yeah.
Thank you. Yeah, thank you very much. Oh, we have a gift.
Maybe I can say something. I mean, yeah, I mean, with artificial intelligence, we also have specialized programs like master programs in neurobotics that tries to combine all these fields. Yeah, for me it was very exciting to see Chile, to see how the people live here, and I will still be here for 1.5 weeks, and for me, so far it was very enjoyable, and thank you for all that experience. For example, when I arrived here, I took the wrong bus, and I exited in Terminal 1 instead of Los Jerez. And then I was guided by somebody, and it was so nice. Yeah.
Yeah, thank you, Fred. We have a gift for you. This is a gift of the Facultad de Ingeniería, so it's a little token of reminder. So that's your piece. So thank you very much. Thank you, everyone, for coming. Oh, we have.